Hello everyone. In this video, we're going to learn how to model a self-supporting telecombinations automatically according to a specific standard. We'll also learn to run the analysis and display the different graphical and numerical analysis results. Finally, we will generate a report including all the input data, loading analysis, and design results of the model. First, we start by creating a new file. Because we are not going to use the grid, we click on the grid command. We uncheck Show this grid box to hide the grid from the screen. In this example, we are going to use imperial units. We click on the unit system command to set the imperial units as default. Also, we will change the length of the units from inches to feet, and we will set the stress units to KSI. Next, we will click OK to validate. The way the model will be generated and the way the design parameters will be computed depend on the selected standard. Thus, the first thing to do is to specify the standard in use. In this dialog box, we select the TIA 222H standard from the drop-down list, and we choose a three-sided tower shape. The shape parameter in the Design Codes and Standards parameter command defines the shape of the tower that we can generate automatically using the SAFI TSC Tower Generation Wizard. We then click OK to validate. The next button on the Tower Telecom toolbar is the Definition of Bolts button. The bolts dimensions and design properties are specified in this dialog box. SAFI TSC provides many libraries of standard bolts. For this example, we select the 5/8 bolt from the ASTM A394 Type 0 library. We then click OK to validate. The next step will be to define the connection schemas that will be used in this model. This command is used to define the layout of the bolts that will be used to connect the members of the structure, and it will be used to check the block shear, bearing, and tear-out failure of the bolted connections. This connection schema will be assigned to all diagonals and horizontals of the model. We assign the bolt and choose the direct, diagonals, and type of connection option. Then, we define the dimensions of the layout by specifying the end distance, the bolt spacing distance, and the edge distance. Finally, we rename the tab by double-clicking on the tab's name. We then click OK to validate. The anchor rods are assigned to the column upon defining their location. Thus, the anchor rods must be defined prior to locating the column. Click on the Next button of the Tower Telecom toolbar to define the anchor rod parameters. For each leg, we will define 4 anchor rod anchors with leveling nuts. We then click on the arrow button next to the diameter field. We can then select from this list a diameter of the anchor rod with the associated thread pitch. We select a 1-inch diameter rod from the list, and we select an ASTM A36 material from the Material Selector command. Rod yield and ultimate stress will be filled automatically. Finally, we specify the concrete resistance and the leveling nut distance. Simply rename the anchor rod by double-clicking on the tab name. Now, we are ready to start creating the tower. The first step will be to locate the tower. The first geometrical element that must be defined is the column. The column will then be used as a reference to create diaphragms and connections. The column is located by its center line. The dimensions of the column are not defined at this step, but it is only necessary to specify the position, X, Y, and Z, of the column on the ground and to give it a name. The column is located at the origin, which is the default. Simply rename the column and then select the anchor rod in the anchor rods list. We then click OK to validate. Once the column is located in the space, we can then specify its dimensions. The column shape is determined by the use of a number of trapezoidal segments which, combined together, will form the column. Don't forget to save the model. The software automatically saves the model every 10 minutes in a backup file, but it's a good practice to keep in mind. Once the column is located in the space, we can specify its dimensions. The column shape is determined by the use of the number of trapezoidal segments which, combined together, will form the column. First, we add a new tab and we define the bottom width, the top width, and the height of the tower. We then click OK to validate. Then, we click on Generation of the Model command on the Tower Telecom toolbar. We can see that the legs of the towers are generated including the supports. In the column Segment Definition dialog box, click on the Subdivide command to create a new segment at 100 feet in height. The segment on top of the tower has the same width on the top and on the bottom. We edit the width of the segment on the top and the top width of the first segment. We then generate the model again. Now, we can see the difference in the slope of the tower that we created by editing the width of the segments. Now, we divide the first segment to 5 equal divisions using the same subdivision command. Segments in SAFI TSE are used in the model generation and may be used to calculate the solidity ratio for wind loads. We edit the names of segments in a numerical table using the Advanced Tables editing command in the SAFI TSE software. These commands are available from the command menu or by using the right-click button on the mouse. Don't forget to click OK to validate. We generate the model and we can see that all segments are generated. The next step will be to assign the section to the legs of the tower. From the column Segments Definition dialog box, we can assign the main leg sections. First, we click on the Non-Standard Section command to define the solid round sections of the legs. SAFI TSE has an extensive list of non-standard sections. We enter the name of the first section. Then, we select the material. The section type, in this case, is a circular section. Finally, we enter the radius of the section and click on Add button. We then click the Close button. The other sections will be created using a duplicate command in the Non-Standard Sections dialog box. It is important to recalculate the properties of non-standard sections when we edit the dimensions of the section. Now, after we are finished creating the sections of the legs, we can assign the main leg sections for each segment. We can do it manually in each segment tab, or we can edit the section column in the numerical table. When we are done, we click the OK button to validate and generate the model again. We can see graphically that all the legs have assigned sections. Before creating the panels, we will define the angle sections that we assign to the diagonals and horizontal members. We display the section toolbar and we click on the Standard Sections command. Adding a standard section to the database is a straightforward procedure. We select the material and the library name. Then, we select the section shape and the section name. We add the other section in a similar way. We then click the OK button to validate. We are now ready to assign the panels to the faces of the tower. First, in the Column Face Prototype dialog box, we rename the current face tab. Then, we add the first panel by clicking on the Add Panel button on the top. We select a panel type from the panel library and specify the height of the panel. A preview of the tower face with panels is shown on the left side of the dialog box. We can increase the number of repetitions if we have similar panels. Next, we click on the Section button to assign sections to panel members. Because we already added the sections to the database, we simply select the sections from the drop-down list. Then, we define the connection parameters. We specify the number of bolts at each member end and the connection schema. Then, we click OK to validate. Now, the first two panels are fully defined. We continue adding the other panels in a similar way. We click on the Add Panel button, and this time, the new panel will have the same parameters as the one selected on the list. In this case, we just edit the sections for the second group of panels. We don't need to edit the connections because they have the same parameters. We can always edit the panels in a numerical table at any time. We click OK to validate the new face data. The last step required to generate the panels is to assign the face to the tower faces. SAFI TSE allows the user to assign different faces to the tower. Usually, this is the case for transmission towers. We assign the face to the column face using the column faces identification command. Finally, we generate the model again, and we can see that the tower is generated including all of the panels. Now, let's add some discrete attachments to the tower. First, we need to define the properties of each attachment. We click on the Antenna Definition button on the Telecom Tower toolbar. The first appurtenance in this example is a dish. SAFI TSE provides an extensive library of dishes. We select one dish from the database. All the properties of the dish are already defined, including the diameter, appurtenant area, weight, and properties including ice. To add the dish to the model, we use the Add Antenna command in the Addition toolbar. Then, we click on a reference joint in the model where to attach the dish. In the Spatial Object Attribute dialog box, we assign the dish properties to the spatial object. It is possible to add an offset to the dish in the three global directions. We can display the attachments including dishes, antennas, and feed lines in a solid form, and we can change their color by changing the display options of spatial objects. It is also possible to change the display color of each of the attachments individually. The second appurtenance is 9 similar antennas, where we attach 3 of them to each face. We open the Antenna Properties dialog box. This time, we add a custom antenna. A generic type of discrete attachment where all dimensions and properties are user-defined, including the normal and transverse area for the wind force calculation. The loading of the antenna will be multiplied by a number of attachments. In this case, we define the number of attachments equal to 3, which means the wind loads, the ice loads, and the dead loads will be multiplied by 3. Then, we attach the appurtenance to the tower in the same way. However, this time, we're going to edit the position of the attachment. If we set the reference joint ID to 0, we can edit the global coordinate of the antenna. We specify the joints of 2 legs of the face as attachment joints, which means that all of the antenna loadings will be transferred to these joints. The last step is to copy the loading of the antennas on the 2 other faces of the tower. We will use the Rotate Copy Extrude command on the Addition toolbar to create 2 copies of the attachment. We specify the rotation axes and the rotation angle. The linear attachments can be generated automatically when we generate the model. First, we define the properties of the linear attachment in the Linear Attachment Properties command on the Tower Telecom toolbar. We then select a feed line from the SAFI TSE library of feed lines. We specify 9 as the number of feed lines. Then, we open the automatic Linear Attachment Definition command. We select the feed line properties from the drop-down list. We select which face the feed lines will be attached to and the base and top elevation. Next, we click OK to validate. We then generate the model again. Now, all the appurtenances are defined, including the dishes, antennas, and feed lines. It is now time to generate the loads and the loads combinations. First, we display the General Loads toolbar. We use the wind and ice load generator to automatically create all the basic loads, the loads, and the load combinations. The wind and ice loads generator command automatically creates the dead load, wind loads, wind on ice and service, ice load, thermal loads, and load combinations according to the selected distribution method. We then click on Generate. We can then see on the screen all the generated loads on the tower. It is possible to display one or a selection of basic loads by changing the display options of loads in the Load Visibility command on the camera toolbar. Another way to display the loads is the numerical tables. The first button on the General Loads toolbar is for basic loads definition. In this table, we can find all the basic loads. The next button is the Load Combination command. Load combinations are a combination of unfactored basic loads with load factors. A basic load with a load factor of 0 will be ignored for a given load combination. It is not part of this load combination. SAFI TSC provides detailed wind and ice table loads, including all factors used to compute the wind pressure and ice thickness. To display wind loads on the tower in numerical tables, we can use the commands member wind loads, surface wind loads, antenna wind loads, and linear attachment wind loads in the General Loads toolbar. In this case, the different numerical results can be filtered before being displayed. Depending on the requested type of results, the filters will be activated or deactivated, such as elements and basic loads. Ice loads on the tower are available as well in numerical tables. We use the commands member ice loads, antenna ice loads, and linear attachment ice loads in the General Loads toolbar. Click on the button to analyze the model and check the design according to the TIA 222H. Other types of analysis are also available in the SAFI TSC, such as p-delta analysis, nonlinear analysis, frequency analysis, buckling analysis, and seismic analysis. Now go ahead and click on the Run. Graphical analysis and design results in SAFI can be displayed for all load combinations or a selection of them. We can select which load combination will be displayed from the Load Combination button on the Results toolbar. This dialog box can be left open while displaying the graphical results. We check the box in the Analysis section of the Results toolbar. We can see the internal deformations are displayed on the tower. Different analysis results can be displayed graphically, such as the internal forces, reactions, and stresses. Another interesting way to display results is through animation. Press the Animate button on the Static Analysis dialog box to start the animation. Analysis results can be displayed as well in numerical tables. The numerical results may be filtered before being displayed. It is possible to restrain the displayed results to the selected elements or to display them for the entire model. It is also possible to display the results for a specific load combination. In addition, we can display results on individual members using the Analysis Element Results on the Results toolbar. This command allows us to view the selected results at any calculation point in any element in the model. The window is made of a graph and a table. The Settings button allows you to change the graph title and the axis titles as well as the title fonts. The two print buttons allow to respectively print the numerical results table and the current graph. The Copy button allows us to copy the image of the graph to the clipboard for use in external applications. We deselect the Analysis Results checkbox in the Analysis section of the Results toolbar. We also check the box on the Telecom Tower section of Results toolbar. The design check results are presented under the form of colors corresponding to a percentage of design criteria. To display the results, select the type of results wanted in the upper section of the Tower Display Results Options dialog box. It is possible to modify the display colors by double-clicking on the color rectangle to modify. The percentages of criteria associated to various colors can also be customized. It is also possible to view the numerical results for limit states for the entire structure or a part of the structure through tables. We click on this button in the Telecom section of the Results toolbar. Then, we select from the displayed menu which type of limit state to view. Any results table in SAFI can be exported to an Excel spreadsheet by selecting the command Generate Report from the menu table. Finally, we finish this example by generating a report of the model. To do that, we click on the Generate Report command. The Model tab determines which input data will be included in the report. Check the boxes corresponding to the data which should be included in the report. The Addition fields at the bottom of the property page restrain the results printing to a range of joints, members, load combinations, and, in this case, of a seismic or dynamic analysis to a time range. It is also possible to restrain the results printing to defined selection groups or to the current selection by the list. Reset ranges adjust the values of the addition fields in a manner to include the entire structure. The ranges defined here are valid for all of the tabs. The Analysis tab determines which results of the analysis will be included in the report. Check the boxes corresponding to the results which should be included in the report. The results will be printed for the ranges determined in the Model tab. The Tower Telecom tab determines what results relative to the Tower Telecom module will be included in the report. All of the geometrical data of the model and design results can be included in the report. We can then click on the Generate button. We will have to enter the file name and the report type. The Microsoft Word document is the default report. The other type of reports available are Microsoft Excel worksheet and an unformatted text report. The Word document report contains a table of contents that makes it very easy to navigate between the different sections of the report. Thank you for watching. Don't forget to subscribe to SAFI's YouTube channel and visit our website www.safi.com to stay updated on the latest features of the software.